Today we have experiment number 7. We took 6 experiments. The first experiment deals with significant digits and how to use it, and we measure the length of some students, and we found that when he's lying down is larger than when he stands up, and we apply some rules, we apply some equations, the significant digits rules. Then the second experiment actually dealing with the graphing lab, and this is the skill experiment. It's how to get the skill, how to use the graphing lab, and graphing paper, and how to use the Excel in the graphing, and how to use the statistical method to find the best fits for the straight line. And we also get the demonstration of the R-square and the goodness of fitting. In experiment number 3, we discuss the density using different tools, and actually the aim is how to use the vernier and the micrometer, and how to use it to find the density by finding the weight, by finding the mass of the object, and measure the volume by measuring the dimensions by vernier and micrometer, and how we get the significant digits and how we get the accuracy for that thing. Number 4, we're discussing the vectors and how to use vectors and how we find the resultants in 3 methods. The first method is the graphical method. We use the polygon-gram and parallelogram method. Then we use the analytical method. This is algebraic method. Okay, we analyze the vector to the x component and y components. And my vectors here in the lab was forces acting on some trolley on the inclined plane. And experiment number 5, we discussed the motion along straight line, and we discussed in that experiment the rotational motion, and how the rotational motion contribute dramatically in the calculation of expect acceleration. And we found the percentage error is so compared with the acceleration without using the rotational constants. Experiment number 6 is dealing with the friction, and we discuss in that experiment the static friction and the kinetic friction and the rolling friction, and we find the coefficient of friction by that way, and we understand what's the meaning of the deep concepts of friction, because it's not easy at all. It's contribute in our life, and we should understand that thing deeply. Anyway, today we have the first experiment in the field of non-constant force. And before, so far, we always use the constant forces. Even in the experiment number 5, the force that make my body move down, rolling down the inclined plane is the constant force. That's why I am using the constant force produce constant acceleration. So I am using the constant acceleration equation, that this is v is equal v naught plus at, x is equal x naught plus, you know that v naught t plus half at squared, and so on. Today we have experiment dealing with the force not constant. Actually, it's a proportional with x, and this is what we call is the Hooke's. So many concepts here behind this one. So I have here spiral spring, and if I connect, this is 100 gram. If I put it here, as you see, I got, let's say, okay, let's say I got this distance. So this is let's say what we call the equilibrium point. This is the equilibrium point, and now my spring is balanced. Here I have weight, and there I have the force of spring. Always force of spring is against to the displacement. I do displacement in this direction of the force of the spring. If I do like this, so I will get harmonic motion repeat itself with a specific time. And this is very nice. And this is the first example of the harmonic motion, this simple harmonic motion, because this happens in one-dimensional motion. Okay, let me check the Hooke's law. We said F is proportional with the force, and mg, I mean g is constant, so if I change g, the x will proportional with m in this case. So this 100 give me this indication. Actually it's 5 centimeters, 5 centimeters, 5 centimeters, 5 centimeters. So this is 100 gram. Okay, now I'll put 200 gram. Oh, this is just to keep in mind. This is 100 gram. It's almost here. Okay, and 200 gram. Oh, it's give me about 10 centimeters. It's nice. Okay, let me check the 300 gram. This is 300 gram. Nice. It's give me another 10 centimeters. So 400 gram. Okay. Oh, it's give me 40 centimeters, and so on. So as I see, this is harmonic motion F, and this is the equilibrium point. Anyway, as I see, when I change the same amount of the, increase the same amount of the mass and the same amount of weight, my displacement change in the same amount. That's why I said, okay, actually my displacement here and spring of the constant up. So I said, okay, F is proportional with X, but in the opposite direction. That's why I put this minus. Okay, and this is actually Hooke's law. It's very important. No, it's Hooke's law. Sometimes we name this experiment as Hooke's law. Okay. Anyway, so here I have some constant, and this constant is equal what? It's K, and we name this constant as spring constant because this is coming from the spring. So this constant related to the spring. So this is spring constant. K, what's the unit of K? Is Newton per meter. So the unit of K is Newton per meter. Okay, Newton is derived unit, so I can say, okay, K is measured by Newton per meter. So Newton per meter. Newton coming from the second Newton's law, and this is acceleration with the mass, and the mass is measured by kilogram, and the acceleration is measured by meter per second square. This is on the m, cancel m with m, so I got kilogram to second square. So actually K is measured in Newton per meter, or it's measured by kilogram per second square. The two units are the same units. Newton per meter is equal to kilogram per second square, and we prove that. So here I have K, and as you see, we prove that dramatically if I measure it. I don't want to go to find K in this case. Actually, I'll find K in the other case. Now, if this is the equilibrium point. If I make this, so I have what? I have harmonic motion. And it's very nice. Simple harmonic motion, because this happens in the, I have so many things harmonic motion. When I walk like this is harmonic motion. Okay? And when I walk like this is harmonic motion. My leg make harmonic motion with harmonic motion. If I said yes, nice, yes, this is harmonic motion. If I said no, it's harmonic motion. And so many things in our life is harmonic motion, but actually we said this is simple if this happened in one dimension. Anyway, this is harmonic motion, means this repeat itself with time. So if I try to do that, but I fail. I try to, to connect some pen here. Okay, so when this is moving like this, pen will move like this. And then I will bring paper here with constant velocity and connect it and draw it here, make it in this direction. So what I will get like this motion. Let's say this is my, this is my motion, okay? And then I draw the paper in this direction, or in this direction, sorry. So I will get like this motion. And this is actually sine wave or cosine wave motion. That's why simple harmonic motion produce sine wave motion. What I have some concepts is very important here. We should take it into account. You see here, we said this is the equilibrium point. This is the equilibrium point. So this represents the amplitude. A represents the amplitude. As you see, here the amplitude is the maximum. This is the amplitude is the maximum displacement from the equilibrium point. So this is the amplitude, and the amplitude sometimes up, sometimes down. Actually here we said F is equal minus K X. F itself is what? Is M with X double dot, because this is what? This is the acceleration. Second derivative of X is equal minus Kx. Actually this is the differential equation. The solution of this differential equation is omega equal square root K over M. And omega is what? Is the angular frequency. And the solution is what? The solution of this, as you see, is a sine wave or cosine wave. So I said y is equal A sine omega t if I am started. As you see here, it's very nice. Or you can say this is y equal A cosine omega t. So this omega is equal K. If you substitute this in the equation there, so you will get that omega is equal square root of K over M. This is very important quantity. The omega mean the angular frequency, and this is equal 2 pi over T, and this is the period. This is angular frequency, and this is the period. It's very important. And this is equal, 1 over T is equal F, so this is equal 2 pi F. This is omega and its relation with this, and this relation with this, a general formation for any harmonic motion. Okay, so in all examples, or in all experiments that consist simple harmonic motion, what you want, what you need actually is only to know the omega, and omega here is K over M. Omega is equal 2 pi over T. So this is giving that 4 pi square or T square is equal K over M. And M is what? Is the hung mass. But actually it's not the hung mass only, because the mass itself is not ideal, it's not weightless. It has some weight contribute in this motion. If you want to check it, as you see here, I can do. You see? This is produced by the mass of the spring itself. If this is ideal, I will not get like this motion. So we should be careful. So this is the mass that contribute, mass of the spring contribute in my harmonic motion. We call it as effective mass, M naught. So actually this M represents the hung M plus the effective mass of the spring. This is constant because this property of the spring. This is constant because this property of the spring. So I can write my equation like T squared is equal 4 pi squared over K M capital plus M small. And this gives me equation of straight line. Actually it's not through origin because I have plus here. So if I put T square in second square and mass in kilogram, I will get like this line, and this will, the x-intercept will represent m naught or minus m naught exactly. So do your calculation and find the slope here. As you see, slope here will represent 4 pi square over k, and this is m naught. So x-intercept m naught will equal minus x-intercept, and k will equal 4 pi square over the slope. So get this slope and find. So you can find this from the graph here. This is the graph. How you can find the time of oscillation? Actually, as you see here, this is 1, 2, 3, 4, 5, 6, 7. This is the period. This is the period. So I can use the stopwatch to find these things. So what I mean by this is 100 kilogram. Now what I have here, just to review some concepts, I have sine wave or cosine wave. It's all right. Okay. I have the amplitude, and the amplitude not contribute in the t. As you see here, I don't have amplitude. I don't have wave. If you make small amplitude, okay, or you make high amplitude, you will get the same period. You will get the same period. So be careful on this, and we don't care about the amplitude here. We care about only the period, because this is from the period I can determine the k and m naught. M naught is very important, and we need here m naught, and the k is very important because, you know, this is contribute our life. Now, if you check the frequency here, I have the frequency. Now my sound, it has some frequency, so you can hear it. Okay, this is going with the wave and to your ear, and you can hear me. Even the light, your eyes and this thing, it's electromagnetic wave, and electromagnetic wave is what? Is the harmonic motion. So just think about it. Everything around us is harmonic. It's very important concept, and here we are taking one example. I will give you something, it's very amazing, just to know, some example, just to know. This is very nice thing. As you see here, it's the ranging of the hearing. See, frequency range of human hearing, and this depends on the harmonic motion. If this make frequency that I can hear it between 20 or 20,000 or 15 and 18,000, some studies that study the hearing range, and actually it also depends on the age. So my age is about to hearing from to 13 kilo or maybe 12 or maybe 7,000. Even I read in some website that there is some mobile rings that you can hear it, but your instructor in the university and this thing cannot hear it, and this is about 13 kilohertz, and actually I cannot hear at that frequency because, you know, this is the age problem. Okay, but you can hear it, so you can put your mobile in this frequency, and you can, you know, hear the rings and these things, and I cannot. So you can say, okay, my mobile is silent during the lecture. Anyway, so here we have what? Here we have 20, and almost the studies is between 20 and 20 kilohertz. So let's agree with this thing from 20 to 20 here agreement. Now the molecules here, if you think about the molecules here, okay, has 3 molecules, and the connection between molecules is like this. So here I have molecules, and this molecule is vibrates like this, and actually the temperature is measure the vibration energy of this vibrational energy of this. Temperature is the indication or give me some information about what the vibrational energy inside, it's high or low. Okay, so here I have, molecules. So if I connect another spring here, so this is another molecule, so this is the force between molecules. It's like this. Now I have molecules inside, it's moving like this, but actually this I cannot hear it because the frequency here is not in my range. But if I, let's say, if I put this one, okay, if I put this one, and let's say I push the molecule from here, so what's happened, this will go back, but this is the frequency here, I cannot hear the frequency. So like I push the atom here by this, okay, so this atom will push another atom and will make like this vibrational, okay, and then go to the end and then come back. Okay, so this is what this is 1 period, 2, 3, 4. So I have what I have like wave going back to the sine wave. Okay, so if this sine wave or with some frequency that is in my range, this range between 20 and 20 kilo, okay, so I can hear it. So let's try. If the frequency of the molecules or the springs inside here, the small, very small teeny springs inside, make frequency that I can hear it here. So let me try and see. See? Yes. Again. See the sound? You hear the sound? Okay. Nice. And this depends actually on the length of this rod. So if I change the length, definitely I will get another frequency because the length will change. And this will take it in the later on in the chapter 13 when we are discussing the young modulus. This is not our joke is here. Oh, nice. So all musical strings and all musical materials depends on these things, depends on the idea of spring and what the frequency can produce by this. If I tighten the string, I got another frequency. If I make it easier, I got another frequency. Today I will get the K and M naught because I know the K and M naught for some spring. I can make or design so many devices like the balance. When I weight myself, the balance with this spring, actually there is some spring inside and I know it's K and I know it's M naught, so I can measure my weight by deflection pointer because this deflection pointer connected with that spring and this is specific value of K. So K is constant, so I can use it anyway. This is the complete period. Go back 1 is the complete period or the complete cycle. Okay, so this represents T1 over F. This is F is equal omega over 2 pi because omega is equal 2 pi over T. I want to find K. I want to find K and M naught. I want to find K and M. So I will use the graph paper. And I will use the Excel software. In the graph paper, just plot between. Take different M's and get the different T squared is measured in second squared is measured in kilogram and got the slope from the graph paper and got the M naught Actually, this represents M naught. So M naught is equal minus K. Enter, set on the graph, and K is equal 4 pi square over slope. Why? Because the equation here actually is t squared is equal 4 pi squared over k m capital plus n naught. This is in the graphic, so you should do it. Okay. In the Excel, actually I have two graphs. One for this equation, this is t squared is equal 4 pi squared over k. With m capital plus 4 pi square over k with m naught, and this represents exactly y is equal ax plus b, so b equal this, a is equal this, and a is slope. Okay, but the other graph I want to prove that the relation between t and n is square root, so I know that t is equal to pi over square root of k, and this is square root of n. The relation between t and n is this, some constant with n to 0.5. So I want to check this, is it 0.5 or not? Actually, I prepared the ready-made Excel to check the values of this and to check the percentage error of this. So here you should plot between t, not t squared, between t, and this is s, and here you should make the kilogram. Okay, you will get some equation like y is equal p x to the power q, like this equation. So check the power of this cube. Is it equal 0.5? Just check this thing. Is a cube equal 0.5? I don't care about p because p is 2 pi over the square root of k. I just want to check the relation. The other one is the same by graph paper. Plot between n kilogram and t squared in seconds. And you get some points, read it, and then you get the straight line. Okay, this straight line will give you the equation of y is equal ax plus b. So as you see here, 4 pi square over k is equal a, so k in this case will equal 4 pi square divided on the coefficient of x. Coefficient of x represents the slope, okay? And as you see here, 4 pi square over k mean a n naught is equal b. Here, a n naught is equal b. So I can say n naught is equal b over a. So this is from Excel. Get this from Excel. Get this. So this is what this is how to supply experiments. Now, and here I will start with the calculation. So I will cancel this. Okay. So this is the Excel graph, it's already made. Actually I designed this one, so here connected for 1.1 kilogram, this is 100 grams, so this is 0.1 kilogram. So I will don't make very high amplitude because there is no effect for the amplitude on the oscillation time. So I will make very small one and start at this point. So let's start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 13. Exactly. Don't know why. Let's start again. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 13.07. This is for point 1. Take it and now start with point 2. Gram. This is actually 200 gram. I have here 200 gram. So make very small amplitude because I don't need. So I will start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 18.09. Again, we start and now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 18.15. Okay, this is 20 oscillation. Okay, restart, and I will measure now 300. So this is the 300. Okay, restart. Nice. So I will start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 22.00. Okay. Again. Now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, it's exactly 22.00. My response is good. I don't know if it's good or not, but let me check the 400. This is the 400. Okay, as you see here. Okay, I have this. So now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 25.25. Reset and start again. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Actually, my response today is good. It's 25.25 also. Don't know. My response is good like this. Okay, so now it's take the 500 gram means this is 0.5 kilogram, and let me check this one here. So okay, let it move and let's calculate it. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 28.03. Okay, again. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 28.00. Okay. Now let's try the 600. So this is the 600. You see here. It's very okay. I will take it here. So let's start from the highest point. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 30.53. Okay. Let's again start. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's 30.44. Now, as I see here, I have what? So if I check the power, it's 0.47. It's good. I mean, T with N give me power. It's 0.47. So this percentage of 4%. So this is good. Good. I think it's good. And as you see, when you calculate the K, this is A. A is 3.8046. This is 3.8046. So when you divide 4 pi square, divide to 3.8046, and this is the coefficient of the x, you will get K is 10.4 kilogram per second square. 10.4 kilogram per second square. And M naught, here M naught is B over A. B over A means 0.0584 divided on this 3.80, and you will get that the M naught is 0.0153 kilogram, means about 15.3 kilogram, and this is very logic. You see the goodness of fitting is 90 99.9%, so it's good. And you see here the power is 0.48, and this is, you know, this is power. Power is very nice fitting, and as you see here, R square is 1. R square is 1, and this is giving me indication that this is not exactly 0.5, because I have here plus M naught. So our job is good. The goodness of fitting, as you see, R square is 99%, 99.97%. It's almost 1. It's almost 100 here, 100 here. So we have perfect job. You see here, I got 10.4K and M naught. So I know now 10.4 kilogram per second square, or 10.4 Newton per meter. Okay, 10.4 Newton per meter. So if I hung here some 10 Newton, I will display 1 meter. As I said, 0.5 kilograms, about 5 Newton. So I displayed about 15 centimeters. Anyway, M naught is 15.3 gram, or 0.0153 gram. It's very amazing. Graph paper just make the same points and the best fitting, and find from this. And you see here, this is the graph paper. So find the M naught. It's the x-intercept. So x-intercept should be minus here. Maybe you will get minus 0.0105 like this. Okay, so M naught will be plus 0.0105, and the unit is kilogram, because this is on the x-axis, and the x-axis represents M, and this is in kilogram. Okay, and here the slope. Just find the slope here, and the unit of the slope is the second square divided on kilogram. So this is second square divided on kilogram. And K is the reciprocal of the slope, because 4 pi square over the slope. So this will be kilogram per second square, and you will get K almost about 10, or around 10 in Newton per meter, or around 10 kilogram per second square. What I have in conclusion, I got the power is 0.48 with 4% error. So I satisfy the equation, almost the equation that told that t squared, or t is equal to some constant here, constant with n to power 0.5. So 0.5, I got 0.48, so this is good. So I satisfy the equation with the percentage error, and because of the M naught, I cannot get exactly 0.5, and this is logic. Discussion. If the amplitude of vibration of a spring is doubled, as I say, if the amplitude is doubled here, I make this, okay, I make this amplitude, okay. Now if you make, now just calculate it by logic. You see, this is 1, 2, 3, 4, 5. Okay. Now let's double the amplitude. 1, 2, 3, 4, 5. As you see, I got the same period. I mean, when I said 1, 2, it's the same times. 1, 2, 4. So there is no effect for the amplitude to the period. And this is very obvious from the equation, that I know that t squared is equal to 4 pi squared over k m plus m naught. No mention, there is none here, no A, no amplitude. So there is no effect of A on my equation. Choose endpoints or equilibrium points for each. This is the endpoints. Okay, this is the endpoints, and this is the equilibrium point. Equilibrium point when this is the equilibrium point, or let's say this is the equilibrium point, and the endpoints. This end, this end, this end, this end, this end. When the velocity is 0. Okay? So he said, at which point does the mass of the vibration spring have the greatest acceleration? I know, and this is logic in all harmonic motion, that force proportional with what? With x. Force proportional with x. I mean, when I have maximum force, I will get the maximum x. Okay? So, and force produces the acceleration. So when I have maximum force, because you know F is equal to ma, as you see, so when I have m is constant here, so A will change during or according to force. So at which point does the mass of vibration have the greatest acceleration? Actually, have the greatest acceleration when I have the maximum displacement from the equilibrium point. I mean, at the ends, I will get the maximum because I can feel it now. I can feel it here. If I do this, I can feel the force. So this is the acceleration, and this is the maximum at the ends. Okay, this is the maximum at the ends. At this point, see, it's the maximum here at this end. So actually, this one at the end points. Okay, at which points does it have the least acceleration? Actually at the equilibrium point, because x is 0 and then force is 0 and then acceleration is 0. At which point does the mass have the largest force exerted on it? As we see, like acceleration. So when I have the greatest acceleration, I have the greatest force exerted on it. At which point does the mass on the vibrating spring have its largest velocity? Largest velocity, as you see here, see, going up, down, going up, down, going up, down, as you see here, velocity is at the end is 0, and an equilibrium point is the highest value, but it's coming, and then slow down, and coming, slow down, coming, slow, you know, increasing to the equilibrium points, and then decreasing to be stopped here, and then increasing to the equilibrium point, and then decreasing to stop. So I can say this is at the end it has the smallest velocity, so at the equilibrium point has the highest velocity. So this is the answer of this question. You will do this experiment on the moon. What's the result of spring constant K in this case, and what? Actually, we said constant spring constant K. This is the property of spring. I mean, this spring now it has some K, and I found this K as 10.4. And as I know that the K is the constant of proportionality, because we said F is equal minus Kx. When I increase F, I increase X. When I decrease F, if I do it on the moon, by the weight of V, so X will what? Will decrease, but K is the constant of proportionality, and I am not changing the properties of the spring itself. So, no effect. Why? Because K is constant. K, we said it's the constant. So, what's the effects? This is additional. Well, how can I change K? I can change K if I change the spring itself. Let's say if I cut the spring. Okay, if I cut the spring, okay, I will change the K. If I make this, the diameter of spring more, I will change K. And if I change the temperature, I will change K because I am changing the material inside itself. I mean, I will change the material itself or the property of the spring. Anyway, this is all what we have for this experiment, and this question number 2 is applicable for all harmonic motion. Always in harmonic motion, I have the greatest force, greatest acceleration, and the greatest displacement at the ends. At the ends, it says I have this at the ends, okay, and I have zero force, zero acceleration, zero displacement at the equilibrium point, but I have the greatest velocity. At the ends, what I have at the ends, I have velocity zero, but in equilibrium I have the greatest velocity, and this is for all harmonic motion. For the spiral spring, for the simple pendulum, it's the harmonic motion, and we have later on angular harmonic motion, and we will take it. And also we have the same thing at the ends. I have the greatest force, the greatest acceleration, the greatest velocity, the greatest displacement, and zero velocity. And in equilibrium, I have zero acceleration, zero force, and zero displacement above the greatest velocity. And thank you.